Hello, everyone. This is Michael. I am going to demonstrate a Polycom, well, formerly Polycom, now Poly, paging, multicast paging application that I wrote. This is in Rust. It is my first real application written in Rust. It is one of my first. I think it's my second application in any language that does networking at all. And this does UDP and it does some very specific protocol. The protocol is the Poly paging protocol. It runs on Multicast. On you can see down here. It's on. That's the address and the port. There's a. Let me see. I'm gonna pull up the reference I have. I can't show it though. Where did I put it? There's an engineering document that was released by Poly. I am not affiliated with them in any way, by the way. It is Engineering Advisory 70568 Polycom UC Software PTT / Group Paging Audio Packet Format. This document describes the Poly paging protocol in great detail. I used that document in order to write this Rust program. So this is all my own code. Furthermore, let's see. Let's just get into it. So what we're looking at right here is just the main process. This is what you run. Well, actually, let's do this first. Let's give a demonstration. Sorry for jumping around so much. I don't do scripts. So here is my phone, and I'm just gonna build this. There's nothing in the target right now. I do have. Let me just get rid of that and that. I built it on a couple different systems. Okay, clear that out and do cargo build. It's pulling in all the dependencies. All right, it's built. Now, if I look into the target directory and debug, there it is. Target debug, K0HAX poly paging, required arguments. There's the quick help and the longer help. This is neat. This text here is pulled directly from these comments. It's really neat. This, I forgot what library that is. I think it's Clap. Yeah, the Clap library is super awesome for making command line programs because it handles all of this flag stuff for you. Anyway, I'll just run this now with the file name of doorbell.g722. That is raw. So that is a WAV file that I used. I don't remember if I used FFmpeg or SOX, but I'll do this file doorbells CG722. Yeah, it doesn't. FF probe. It's ADPCMG722. It's just raw. There's nothing special about it. So target debug that I'm gonna do tac f doorbell.g722 and I forgot already. The codec -c is G722. If I do like G721, it's like, yeah, no, the possible values are G720, G711 ULaw, and G722. So this is G722. Let's run it. You know what? I forgot to turn that mic on. Let's run that one more time. Hopefully you heard that one a little better. So that's all the script does. It activates or it sends whatever audio file over multicast specifically to this port 5000 on 224.0.1.116. Let's just run through the code. So we get a configuration. We get our configuration. That is the that command line parser thing. I build a builder for the logger. So this is to write these logs. It's like info, whatever. Oh yeah, if we run this, I'll do this one more time, and I'm gonna put 4 V's in front of that for super verbose. And now I get a little bit more detail. That's what this logger line does, or this logger setup stuff does. And then I can do, log.info, or log, sorry, not dot, but whatever, : info, that's a macro, not a function. We do that to print stuff in a nicer way. Yeah, then we grab the contents of this file. So we get the file name as an argument, and we pass that by reference to this from file function, and we unwrap it because that from file function returns a result that's a Rust result, so it's OK or error. And if it's an error, we say what the error was, and then we exit with a error code of 1. And then we get the codec from the command line input, and we convert that from. I guess we don't convert it. We check which one it is, and then we return that as this codec variable. And if it's nothing, it fails and says invalid codec. Then we get what mode we're using. I didn't put a mode flag in because it defaults to transmit, but there's actually two. There's transmit and print. So if that argument is print, it runs polypaging to print, this to print function, which takes the contents of the file, the caller ID name, the codec, and a channel number as arguments. And then if it's a transmit flag, it takes the same arguments, but it's do transmit instead. And that is an asynchronous function, which is why this whole main function is inside of a Tokio or Tokio. I don't know exactly how you're supposed to pronounce that. It's this is an asynchronous main function. So we do that, we transmit, we do an await so that we wait for that to actually finish because that is an asynchronous function. And then we are done and we return OK and the program ends. For the config, here's the whole config struct. If you don't know what a struct is, that is basically a way to, it's a structured memory block, basically. We're saying, hey, this area of memory is structured in this way. It is a file name, which is a string. Before I go into that, actually, you can see here, this command, we've got two little flags. These are for the compiler. One is telling it that this is a parser, which I don't remember which one that was for, and debug. Debug basically lets you get as the programmer, lets you get the insides of the struct easier without having to manually do a bunch of stuff. Then there's this command for the command line parser, or the argument parser, and it's saying include the author, the version, and a verbatim doc comment. That verbatim doc comment means that it's actually including these new lines. If I didn't do that, it would only do new lines for different paragraphs, and I wanted it to be exactly this, just because I think it looks nicer. Anyway, we got our config struct. It's a file name, which is a string, the caller ID name, which is a string, and it defaults to PC. We've got the codec flag, which is an option, and it's actually getting that from another, I think that's an enum value. We'll take a look at that library in a moment, or once we're done with this one. So just keep that in mind. There's this codec flag option. And its default value is G722. And if you notice, this is taking a string type as a default value and just magically converting it into what is an enum. So there's a little bit that we had to do to get that to work, but it's really simple. Then there's the channel number. The channel number, I default to 49. There are, I put in notes here, channels 1 through 25 are PTT, or push to talk, and then channels 26 through 50 are paging channels. Channel 49 is priority, and channel 50, I believe, is emergency. So those two are special. All the other ones are sort of normal. I think you still have to configure them to work on the polyphones, which is not in the scope of this video, but it's not super complicated to enable that either. That takes because this starts with a C for channel, and all these other ones also start with C. For caller ID name, I actually renamed the minus and then a single character thing to N for name. Codec is the default short for C. And then channel number, well, we can't use C because it's the codec, and we can't use N because it's the name, so I just chose U for number, the second letter number. So yeah, that's sort of arbitrary, but it works. And then we've got this verbosity level. This works somehow. I didn't write that verbosity or the library that this is using, so I just took their documentation and took their word for it, and it works. And then the mode, which is another enum, which actually, yeah, it's right down here. You can see here's the enum. And really, it wasn't very complicated to make that work. So the default value is transmit, and it can be either transmit or print. It's just the name inside the enum, and that's it. Like with this derive, that just works. And finally, well, two more things. There's this, I guess this is technically one thing. This is a printable unsigned 8-bit integer vector. This just takes an unsigned, or a vector of unsigned 8-bit integers, which is a number from 0 to 255, and convert, and that's it. So that's what this struct stores. It stores a vector of that. A vector is basically an array or a list. If you know Python, it would be like a list. That's what the struct does. But we implement this standard format upper hex for printable 8-bit integers, unsigned integers, for printable unsigned 8-bit integer vectors. There we go. It's my specific. I made my own type, kind of, and we make this implementer for that format, which takes the arguments itself, this f, which is a mutable formatter that's passed to us by standard format, and returns a standard format result. So we create a brand new string, we make a mutable string so we can change it, called format string or FMT string, and create a new empty string, and then for each byte, that's the variable name, but for each byte in the reference or the referenced self, so that basically just if there's an and sign here, I'm doing another and sign here. I still don't completely understand Rust's borrowing system, but like the compiler told me I couldn't do it any other way, so I did it this way and it works. Self.0, so the first, what is this? This is the first value, or the first thing in this struct, which the struct only has one thing inside of it, and it's this vector of unsigned 8-bit integers. So it can only be .0. If it had more than one thing, it could have .1, .2, .3, whatever. And for each of those bytes, we create another variable, byte string, and this has to be inside of this closure. If it's not inside of here, then or sorry, this let byte string is inside of this closure. So once this closure is done, that byte string is freed. So we can't return that ever, but that's okay. Well, unless the return was inside the closure, I suppose. That's a string, and it is equal to. This is not mutable, so it can't change once we set it. It is equal to this. So it takes the byte that was in here and does an uppercase, an upper hex for it with specifically a 2-byte, or it would be prepended by a 0 if it was like 0, 1 instead of just saying 1, just to make it more readable when the whole thing is printed out. Then there's a format string. Or then it pushes that, it takes this variable and just puts it on the end of the format string. And it just does that for everything. And then it sends that back out to F. Okay, that was very complicated for something that is relatively simple, so I'm going to try to get through this faster. Let's go over to the library. This is where all the interesting stuff is happening. I'm going to probably skip that last part. Let's cut back over. Don't need that on the screen this whole time. Okay. So this is the RTP specific code, as you can see from my comment. And this is an array of bytes that makes up the raw RTP payload. So here's a vector of an unsigned 8-bit integer, just like the other struct, but this one's called the RTP payload. So we can determine its type. And also just so that this library, because this library doesn't know about that other string type, or not string type, that other vector type. It only knows about this type of struct. I'm confusing types and structs, and I'm sorry. I don't know the correct language to talk about it correctly. Then we implement this format upper hex. This is basically doing the same thing as the last one, so that we can print it out easier in later functions. I'm just going to move this up. And then this is the polypaging specific code. This is an enum for the opcode. There's 3 opcodes in the document. There's alert, transmit, and end. So every page is preceded by a bunch of alert packets, and then after the alerts are done, then the bulk of the page is a bunch of transmit packets. And after the transmits are done, there's a bunch of end packets. And the alert tells the phone, hey, get ready to listen. I'm going to be sending a page. Are you okay? Are you ready? Here it comes, because this is UDP. Because it's UDP, there are no acknowledgements. It's just blast it out and hope everybody gets it. So we send a whole bunch of alerts, then we do the transmit, which has some redundant data in it. Which we'll get to, and then we do a whole bunch of ends to say, like, we're done, no, really, we're done, yes, I mean it, we're done, and it sends that enough so that the phones will stop being in paging mode. This enum is just my programmer representation of these 3 opcodes, but then I actually define these opcodes by hexadecimal bytes. In this implementation, there's implementation opcode to unsigned integer 8-bit unsigned integer, which takes self and returns an unsigned 8-bit integer, and it matches on this enum. So if it's an alert enum, it returns 0x0f. If it's transmit, it's 0x10, and if it's end, it's 0xff for 255. And I also implemented a display formatter for that enum just to make it a little nicer if it gets printed. This one will show what it is and the hex code, and that's just hard coded because it's 3 lines and it's not a big deal. Let's see, paging supports 2 codecs. Select the one you're using. Oh yes, so here's the codec flag. This is another flag. It's another enum. There's G711 ULAW. And there's G722. Those are your only options. there's the two 8-bit unsigned integer implementation for that. G711 is 0x00 and G722 is 0x09. And the display formatter also. Same deal. Let's see. This information doesn't change during a session, so we can pass it by reference to other functions in the library. This takes a session info with a lifetime. Now we're getting complicated. It takes a lifetime. A lifetime of tick A, and it needs that for the caller ID. I don't remember why that needed a lifetime. Probably because it's a string, but it's not a capital S string. It's an str, which is a different type of string that doesn't have a bunch of magic, basically. So it needs a lifetime, and that's why it needs a lifetime, because it's a borrowed string, and we're going to be passing that around a bunch, so we need to keep track of who the top level owner is, basically. The header and trailer packets in memory representation. Oh yeah, so these are packet no payload. Keep track of these two structs. These two are kind of special. They're not super crazy, but again, we have this lifetime of tick A because the session info has the lifetime of tick A, and the compiler will yell at us if we don't keep track of that, because it doesn't know what to do otherwise. So we're sort of telling it this is what I intend. Anyway, it takes an opcode and a session info. The session info, I totally glossed over this, has the channel number, host serial, caller ID length, and caller ID. The caller ID length is always 13. Always 13. It doesn't matter if you send a caller ID of 1 byte or 0 bytes. It's always 13. That's in the documentation. I don't know why it's in here, but that's what it is. It's just always 13. And then, obviously, if your caller ID isn't exactly 13 bytes, it's not allowed to be longer than 13 bytes. I don't know what happens if it's longer. If you make it longer, I have a suspicion of what happens. And I think it will run into your payload. Well, I think your payload will try playing your caller ID, basically, which would probably just sound like garbage. Anyway, your caller ID must be exactly 13 bytes. If it's less than 13 bytes, you pad the end with zeros. And we'll get there. The packet no payload takes opcode and session info. That's it. Then the payload packets. That also is, tick A lifetime. It takes an opcode and a session with a lifetime of tick A. And also, it takes a codec, flags, which I didn't see any, I don't know what those are for. Those are extra special. I always set them to 0 and everything works fine. I don't know if they're documented, actually. Let me just scroll through here. Yeah, flags. 1 byte. Oh, it's supposed to be 6F? Well, it's not. But it says notes not applicable, so whatever. I set it to 0 and that works, so whatever. Sample count. That is the RTP stream, which is this payload down here, this RTP payload. This sample count is the RTP stream timestamp of this packet, which you have to calculate. And because this program always sends fixed size payloads, it just calculates that in a dumb way. It works, it's technically correct, but because it's a static, because this payload is static, I don't bother trying some fancy, measure how many bytes we're sending and then figure out what the timestamp is. I just figured it out once and said, that's it, and then hard-coded it. Right, packets with both, and then packets with both, or both with, and without a payload must implement these traits. So this is the trait of a packet. Both packets with payload and packets without payload, they're both packets. and they implement print, debug, and 2 bytes. 2 bytes is the important one. That's the one that converts it into something we can send across the wire. Debug is a less readable form. Is it less readable? It's a different form of basically what print does. Print just makes it, print does a nicer job of printing what the packet is. We have to create a couple of errors. If the caller ID length is wrong, basically if it's longer than 13 characters, we need to throw an error. So I create a caller ID length struct, which has nothing inside of it, and implement a display for it, and say that it implements, or suppose that caller ID length implements a standard error. And if you print that error, it will say the caller ID must be 13 characters or fewer. There's also a channel out of range error. If you enter a channel that is not between 1 and 50, it throws this error. Same thing. And finally, we implement the packet trait. This is where a lot of magic happens. So, first, this is for packet no payload. And it takes a lifetime because packet no payload takes a lifetime. But it takes the anonymous lifetime because it can. Again, I did stuff until the compiler was happy, and it works now, and it doesn't crash because it really is hard to make a program in Rust that crashes in a dangerous way. If you can get it to compile, it's pretty solid. I did crash something, but not because of a memory problem. It was because I didn't handle an error, so it panicked. But a panic is okay. It doesn't segfault. Segfault's bad. Anyway, this is going to print the contents of the packet in a nice way using printline. So this does let caller ID ASCII. I don't actually remember this. I wrote this code last week, and I can't remember stuff that long, so I'm relearning it as I read it to you. It takes a caller ID ASCII result, which is it's a result of a borrowed ASCII string, or which would be the OK value, or an error value of an as ASCII string. Oh, so this is converting, This is converting the caller ID from whatever format you gave it to the program in, which is probably UTF-8, into ASCII. The caller ID must be ASCII. Again, that's what the documentation says. Then we take that result and basically we manually unwrap it. This whole let thing could be replaced by just getting rid of this underscore result and like putting a question mark here, but I didn't do that. So this is what you get. I'm not going to go into why that would work. I'm sure that's somewhere else in my code here. And we let the mutatable means you can change it. Does that need to be mutatable? Yes. So this is creating a 13-byte long array of unsigned 8-bit integers. So this is creating a specific size array. It's exactly 13 bytes long and filling it with zeros. So it starts out with zeros, and then we create an I equals 0, which is mutatable for this loop we're going to be doing. And it says, okay, if the caller ID length is greater than 13, throw that error. Otherwise, for each character in that string as a byte, we saw that as bytes implementation above. Actually, no. The ASCII character string, this ASCII library here, has a function called or a method called ask as bytes that returns exactly what we need. It returns I think it's a vector, but it doesn't matter, of unsigned 8-bit integers for each character in that string. Important note, there is no null terminator for Rust strings, so we don't have to worry about that. Okay, so it takes that and it uses the I to index the array we're putting that byte into. And we're dereferencing. This is actually returning a reference to that byte. We're dereferencing that and putting the actual value into this array at the location of I, and then we're incrementing I. So if you have a 2-byte long caller ID, it will run through this twice, and you'll end up with the 2 bytes in this array, and the rest will be zeros because of this initialization. Finally, we print out all the information. So the opcode uses that formatter, so I don't have to do anything special to print it. It uses the formatter in for the formatter for the enum channel number. That's just a unsigned 8-bit integer, which you can just print. The host serial is, I don't remember. Oh, I think that's just, that's just an 8-bit, or sorry, that's a 32-bit unsigned integer. And we can just print 32-bit unsigned. We can print the primary types as is. This one we use :x, so that will print it as hexadecimal. Otherwise, it would print it as a number, which is less useful. It'll print the length, even though it's always 13. It's going to print it anyway. And where's it even getting the caller? Whatever. Oh, I remember. And then the caller ID is printing the ASCII format, which is the one that we just got up here. For debug, it does sort of the same thing, but it's not going through the hassle of converting the caller ID to what basically we need in order to send it out as the actual packet. Okay, finally, this method convert the 2 bytes function. This method, I suppose. This method converts the packet struct to an array of unsigned 8-bit integer bytes to be transmitted over the network. So this takes our packet with no payload and creates something that we can just send out UDP. We get a vector because we're not sure how long this is. I think we do know how long it is, but it's just good practice to use a vector, so that's what I'm going to do. Plus, they're easier to work with for sure. We take a vector of unsigned 8-bit integers, and then we just start pushing stuff to it in the correct order. So we take the opcode represented as 8-bit integers, and we push that onto the vector. We take the channel number as is and push it onto the vector. And then for each serial byte, for each byte, we have to convert this unsigned 32-bit integer into 4 8-bit integer, this unsigned 32-bit integer to 4 unsigned 8-bit integers for the host serial. There's a function to do that down here. Oh, getting into my test code. Where is that? Here it is. This black magic that I copied off of Stack Overflow, because it's black magic because it's doing bitwise shifting and stuff. And there's an XOR, I think the ampersand is an XOR. I don't remember. I don't know. Whatever. It does what we need, and it works. Pay no attention to the man behind the curtain. Yeah, so we do that. We get the 8 bits, we get the 8 bytes. We push each one of those onto the value. We push the caller ID length onto the value. And then we do the same convert to ASCII and, create this array and go through all that. And then finally, after we're done creating that array, we again, I don't know why I did it this way. That's kind of dumb, but whatever. Oh, it's because I needed to make sure the length was right. And this was just easier. We go through the reference to caller ID bytes. We push the value of each of them into that vector, and then we return an OK value of the vector. So this OK and result thing, this result, oh yeah, I didn't say what the result of this 2 bytes was. The result of this is a result. Don't get those confused. Result and result are not the same. Even though they're spelled and said exactly the same way, they have different meanings. Thank you, English, and thank you, Rust. Okay, the result, the type of this result is, well, it has 2 types. The OK type, which is always this first one, is if this function returns good, it'll give back a vector of unsigned 8-bit integers. If it fails and it throws an error, it will throw an error of box with a type of dynamic standard error. The box is too complicated, and look it up if you want to know. But that's what you have to do. I don't think... Oh, yeah, I do. So here you can see, like if the caller ID length is greater than 13, that returns an error of box new caller ID length. This error is a result. And this OK is a result, and the value is this first type in the first case, and in the error case, it's the second type. For packets with payload, this is the same thing as the other one. I'm going to skip some of this, probably. Yeah, I'm going to skip that. We'll go straight into the implementation of 2 bytes. For that, we need the codec in 8-bit unsigned integer form. We need the flags, which is just an unsigned 8-bit integer, so it can just go on there. And this is where things get complicated. So we need how does this work? Okay, so the sample count is a 32-bit 32-bit integer, because it can go to a pretty high number. So we have to do that transformation for each byte in the sample count, and then we have to do, basically we have to go through the payload data and clone it. Again, otherwise Rust got mad at me and threw a fit, so I clone it. For each of those payload bytes, we just push that onto the value and return the value. So it's really, from there, that's pretty simple. This the file byte actually takes the file, the G722 file over here, and breaks it into the correct byte order for the paging system for Poly's multicast paging codec, not codec, but protocol to work. It has one thing inside of it, and it's, again, a vector of unsigned 8-bit integers, because that's just a byte, or it's a list of bytes. And it implements from files. So if you say, give me a new file bytes, and make its value the file bytes : from file, and give it a file name, it'll open that file up. That's what it's doing here. It's opening it and reading it into this result and saying, okay, if it worked, great. Return a file bytes with the contents of this file. And that's it. Otherwise, return whatever the error was in this result. And then upper hex formatter, same sort of thing we did before. This is going to take... Where's the byte string? 4 byte in self contents. Yeah, this is basically just giving you the hex of that file. It's pretty dumb, but it works for that. I could have swore there was something else I had to do in order to make this work. Oh yes, there is. Okay. So there's a helper function we looked at before. There's get session, which just returns a result with session info. That struct we talked about earlier. And we don't technically need this function. We could just initialize it in our code somewhere else, but I like functions to get my stuff. So that's what I did here, just to sort of be consistent, because we very much want to use this later on. Another helper object. This one, same thing. It just gets the alert opcode, and this one gets the end opcode. This one gets the payload. The payload, the way that the multicast paging works is in the payload for the big chunk of the packet that is the payload. On the very first payload packet, it's just the first run of bytes for that payload. On the following and all subsequent packets, the payload is what's the order? I want to make sure I get this right. Yeah, the payload is first a duplicate of the previous packet. So you have to remember the payload between packets. You take packet 1, it's got payload A. Then in the second packet, the payload needs to be AAA and then AAB if the second packet would have been AAB by itself. You have to duplicate the previous frame in each frame or in each packet. And that's how it achieves redundancy. It's not too bad, but it does mean that you have to write this craziness. So we have this function which takes a lifetime parameter for the session info, again, and it returns a packet with payload. This is important. This packet with payload has a lifetime of tick A, because we have to keep track of this lifetime. The lifetimes are important in Rust. So it takes a session, codec, flags, and payload bytes. The payload bytes is going to be the thing that we really want to focus on. And it's got this result variable, which is a packet with payload. And we get the payload length and the chunk number. So this is actually not the chunk number. This is the number of chunks. We take... What am I doing here? The length of payload bytes. Do I ever use chunk num? Nope. Okay, ignore chunk num. I don't know why I even have that. Whatever. But payload length. That one's important. Okay. Let me fix. Jumped around incorrectly. Okay, take the payload length. We get that. Oh, right. Okay. So I thought I would need the chunk num. That's dead code. I should delete that. We get a mutable vector U8 for the last chunk. This is how we remember the last packet that we sent, or at least the payload. We don't need a header and all that crap, but we need the payload for the previous packet. The sample count, which starts at 0 in my case. It doesn't need to start at 0, but it's a lot easier if it does. This payload, which is the payload for the current packet, and then the entire packet payload. So this is the header plus the payload. So not, or is that right? I think that's right. Yeah, I think, no, it's the, what's the difference? Oh. Right. So, last chunk is the previous packet. My naming is terrible. I should comment this. Well, that's what the video's for, I guess. The last chunk is the previous payload. The previous packet's payload. This payload is only this packet's payload, not this packet, not the previous packet plus this packet. And then packet payload is last packet and this packet. You probably don't need to do it like this, but this is easier for me to think about when I'm looking at it. And then we do a for loop for n, which starts at 0, in 0 through the payload length. This is how you do a range in Rust. I think it's pretty clean. It's not immediately obvious if you don't know Rust, but it makes total sense. And then we say, okay, this byte. Why did I do it this way? Oh, right. We're iterating over the bytes. We're iterating over each byte in the payload. So we get the first byte in the payload, or we get the n byte in the payload. We check. That's where this 80 came from, up here, this 80. Which I did, this math is stupid and wrong. If n mod 80, so every 80 bytes, we do a cutoff and say, okay, I'm done with this packet, basically. I'm limiting the payloads to 80 bytes, or not the payloads, but the I suppose the active packet's payload. So at the end, like on packet number 2, the payload will be 160, not 80, but you understand. And then also do this bit only if we're not on the first. So, oh yeah, if this is both, if n is both, n mod 80 is 0 and also n is not equal to 0, because 0 mod 80 is 0, and we don't want to do this on the very first packet, then we truncate this payload to be a bunch of zeros. And then if the last chunk's length is not equal to 0, then append the last chunk, which is mutable, but just append that. Append, not push. Those are different those are different. So if this was push, it would push a vector into another vector. So you'd have a vector of vectors. We don't want that. We want a vector of bytes. So this is appending. This is taking a vector and sort of mushing it into another vector. So that's the previous chunk, the previous packet payload, and then append the current packet payload and clone it and whatever. And then truncate the previous payload and basically put the current payload into the previous payload so that we have it there. RTP payload. Not sure. This seems redundant to me. Oh, it's not, because this is putting it into a struct. So we create an RTP payload struct or instance, and we take this payload data and put it in there. And then we create a packet with payload. So this is another struct. We instantiate it as the payload packet. We say this is a transmit packet. We give it the session, codec, flags, and the sample count, and the RTP payload, which is what this instantiation was. And we just go ahead and give that ownership of the payload by not doing an ampersand in front of it. And we push that payload with packet into the result vector. And then once we're done with the, if it's not equal to 0, this part happens on every packet. or yeah, on every byte, even the one that, or not every byte. This happens on the first byte in the payload, and also happens on a nmod 80 byte in the payload. We truncate the packet payload. We make it all 0. Or I think this is truncate to length of 0. And then we increment the sample count by 160. I don't remember how that number works, but that's what it is for this length of packet. It's 160. I figured that out experimentally. And finally, on every byte, including things that are not nmod 80, we push the byte into the packet payload. So the packet payload would get truncated at this point here. So if it was nmod 80, we need to push a byte on after that truncation happens. And also we just need to push the byte on if it's not, nmod 80. And finally, at the very end, we return the result, which... Oh yeah, get payload doesn't return a result. It does return a result. It just doesn't return a result of type result. Oh man, that's hard to say. It returns a vector of type packet with payload. It does not return a result. So like if this function fails for some reason, if any of this stuff in here returns an error type, which I don't think it can. But if it did, then the program would panic. That's an example of a way that you can make a Rust program break, I guess, but it won't break in a way that is not safe. It will just break in a way that makes the program stop. It'll panic because there's no error handler. Okay. We have this function, which is used later again. This gets an array of another array of bytes from get payload to transmit the actual bytes. Do I use that in here? Nope. Yeah, because I think... Nope. Oh, right. So this whole thing... This returns a vector of packets with payload. It doesn't return a vector of bytes. So you can't just use this to transmit directly across the network. Instead, we use this. Is that right? Yeah, sort of. This is kind of weird. This is getting kind of weird. I spent a long time writing this. And again, one of the first things I've written in Rust. And it's kind of rough. We get payload packets, takes a session info. Well, what do I put in my comment? Help the functions to get an array of another array of bytes from get payload to transmit the actual packets rather than the internal representation of an array of packet with payloads. Session info, codec flag, flags, and the data. The data is going to be the payload. This returns... Here you go. There's a result for you. This returns a vector, a result of, in the OK state, a vector of vectors of type unsigned bit integer. In the error state, it's box dynamics standard error. Okay, so we create the vector of vectors. Vec new, yep. Create payload packets. That's a vector of packets with payload, and get payload, and there's our data in there. Okay, this is starting to make sense now. And then we go through each of those payload packets and say, okay, well, for each of these results, get a variable that is the byte representation of that packet, and push it into our result. And at the very there you see I used the question mark semicolon to make my code not terrible to read. And at the very end, return a result, okay result. One other thing in Rust, if you're returning from a function, you can either use the keyword return, or you can just put something like a variable or, you know, whatever you're returning on a line by itself and not put a semicolon. If you put a semicolon, that's different than if you don't. If you don't, it returns that thing on that line. If it's, yeah. Do print. It mostly does what you transmit, but don't actually transmit. Okay, yeah, I'm just going to skip over that because it's not super important, and I've been going for almost an hour. I'm terribly sorry. But you're still here. Why are you still here? Okay, whatever. This one actually does the transmit. Finally, after an hour, we're at the juicy part. Transmit a file passed in as file bytes, or reference to file bytes, to polyphones via IP multicast. This function handles all parsing and timing, as well as IGMP setup to join the multicast group. You don't strictly need to do IGMP setup, but if you don't do IGMP setup, your page may not cross subnet boundaries. It might not cross subnet boundaries anyway if the network isn't set up correctly, which is, by the way, very difficult. I have yet to get that working. So this phone that I'm using as my test is on the same subnet as my computer. It should be able to cross subnet boundaries if multicast paging, if multicast routing is configured correctly, but on like 99% of networks, multicast routing doesn't work right. So your mileage will vary and will probably not be great. Right. So we do the transmit. We get the file bytes. We get the caller ID as a string reference. We get the codec flag. We get the channel. We return an IO result of nothing in the OK state and an error of whatever error, an IO error, if it does error, which it could, especially in networking code, because you might not have a networking card and that would make this error, or you don't have one plugged in or whatever. We have an alert gap. Between each alert packet is 30 milliseconds. Between, what's the join gap? I don't remember why I did this. Oh, yeah. Between when we join the multicast group and when we start doing stuff, we wait a half a second, or 500 milliseconds. Between each payload packet, we wait 10 seconds. These are the not the IGMP one, not the join cap, but the other two. Those are specified in the Polycom engineering document. They changed their name. They're Poly now. Yeah, it's specified in that engineering document. We create a session. This session lives for as long as this function lives. This is that session info. We pass it a channel. We pass it this hard-coded value for the flags. Or no, I'm sorry, that's for the serial number. Yep, I just hard-coded the serial number to be 0 because that's easier than getting the last however many bytes of the machine's MAC address or whatever, which is what it's supposed to be. But 0 works fine, and who cares? It's a one-way transmitter. I don't care. And we pass in a reference to the caller ID, we pass it the same caller ID reference. We unwrap, so this takes that result that this get session passes back to us, and if that result is not an okay result but it's an error result, then we say there's a problem and we quit the program. We get an alert packet, and we get this is get a single alert packet and this is get a single end packet, but they're all the same, so we can just get it once and then just transmit it a bunch of times. And then we get the payload packets. So this is that get payload packets, which returns this vector of vectors of bytes. And we pass that, again, the session codec. The flags this time, again, hard-coded to 0. And the file byte contents. And again, unwrap or else, we say, yeah, that failed. And we exit the program. I guess this is technically, like, this is the type of crash that a panic does. But I wanted to do it. I didn't want Rust to do it. So I did it. Whatever. We open a socket. Now we're getting somewhere. We're doing networking now. We open a socket. We get the result of that. That's what the question mark is for. And we do an await because, again, this is an asynchronous function. This is actually the asynchronous function. We get a UDP socket. We bind to any available network card on port 5001. It doesn't... It actually might need to be on port 5001. I don't actually know. But we do need to transmit on port 5001 to this multicast address. That's the remote address. I don't think I ever use this variable. I guess I do. Why did I do it that way? Whatever. I created these things for some reason. Oh, right. Sock connect and join multicast v4 are different. Whatever. I probably could have done them both the same way, but I didn't. Can you tell I was reading like how-tos? Right, so we connect, we do an await on that connect. That just sort of opens the transmitting socket. We don't actually have to wait for any bytes or anything like that. The join multicast group, I guess that's not asynchronous. Anyway, that'll join the group. It sends an IGMP packet basically from your computer to the switch that says like, hey, I'm like, I care about this 224.0.1.116. Please, if anyone else is sending packets for that, just like go ahead and send them to me too, because multicast doesn't work the same way as broadcast. It doesn't always send to everybody. It only sends to people who the switch, or not to people, to devices that the switch knows are listening, which is to cut down on traffic on the switch. If you're not listening and you don't care, like, you don't need to get the packets. Don't strictly need to do this. Again, you don't need to send IGMP if it's on the same subnet, but it's good practice. Then we sleep for that join gap, which was 500 milliseconds. So we just kind of wait for everything to sort of get ready for us after we say, hey, we're in the multicast group. And we start. We send, we get those the alert bytes. We convert them to bytes. We do the alert debug, which is over here. You can see that's that alert debug. And then we send 32 of those, 31 or 32. I don't know. We do this for anonymous in 0.31. We send the alert bytes with socket send await. And then we sleep for the alert gap. And we do the payload. And this one's a little different. This one's payload packet in payload packets. And then we say, well, the payload bytes is a vector of the payload packet. This is actually under the hood doing a conversion, which is pretty neat. Or no, it's not. Is it? No, it's not. It's just cloning it. We send those bytes, and we sleep for the transmit gap. And finally, we do end debug. We get the end bytes, and we loop through that 12 times. And that's it. And I wrote some tests. This is literally a hard-coded payload. So actually, if I go over here and do cargo test, it ran no tests. Why did it run no test? Oh, I'm in the wrong. This is for the library, not the application. There we go. It ran the tests. It's kind of neat. You can actually say like, hey, this test should fail. If it fails, that's good. If it doesn't fail, that's bad. I think that's kind of neat. This does not have 100% test coverage, but you can see here. Here's the flag that says, like, this needs to panic. Anyway, that's it. Oh, man. I made all kinds of changes, I guess. Anyway. If you have any questions, too bad. I'm not going to answer them because I've already forgotten how my code works. I will post this on GitHub, though. My GitHub is K0HAX. Okay, I hope you learned something. I'm not sure I taught that very well or explained that very well, but just for kicks now that we've gone through that whole thing, I will run this again. Actually, you know what? We never showed. It's a printing mode. There's the payload packets. So that's what it's doing when it's transmitting. You can see, if you actually look at this, you can see, like, this is great, actually. FA, whatever. And this one starts with FA, because that's, like, in the middle of this packet. So you can sort of see how that beginning, or the previous packet is included. I'm really tired, so I'm gonna end it here. I was gonna transmit it, and I bumped my camera for the thing. Okay. One more time, and then that'll be it. I lied 2 more times. All right. Have a great one. This is Michael Engelhorn signing off.